Okay, ladies and gentlemen, welcome back once more. In this lecture room now the last presentation of the day. After that there will be in 2 more lecture rooms still presentations to go to. At the end of this presentation I'll tell you a little bit of what's going to happen in the last bits and pieces of the afternoon, but we're first going to focus our attention on group 28. I will dim the lights for them and then the floor is theirs. And if you take this one for the live stream.
Okay. I should just open it there. Like that, yes. Today's world of aviation is hungry for innovation. The constant need for a more efficient aircraft, slender wings, and new control systems are pushing researchers to create new, slender aircraft structures, make the use of novel materials, and implement new intelligent control systems into aircraft. Before you can put such a system on an aircraft, you, however, need to test it first. And this is where the problem comes. You see, you can test a new aircraft structure in a wind tunnel, which is proven by many years of experience. However, wind tunnels face wall interference, which is an aerodynamic phenomena that is present in wind tunnels and differs the results from wind tunnel from an actual experimental setting. Furthermore, wind tunnels can take long to schedule. It can take months before you can actually reach towards your experiment. And finally, when you get there, you may be surprised that the price of a day in a wind tunnel can be above 40,000 euros. Furthermore, you cannot take it that hard in a wind tunnel because breaking your structure risks damaging a multi-million-euro facility. Then there is a second option, to test it using a small-scale aircraft. However, this has to be a custom aircraft that the researcher builds themselves, and every time they have to reiterate it for an extra test, they spend a lot of time resources before they can achieve that. And finally, when they redesign, then they have to recertify the aircraft again. So the question that the team asked is clear. Is there a third option? A platform that would fly in the real atmosphere without any walls or obstructions. A platform that can be easily modified or upgraded. A platform that can reach high-speed subsonic flight just like in the wind tunnel, and at the same time is easy to transport and fits inside your van. Today, we are introducing that platform. This is Hugo, high-speed, unmanned, general-purpose observatory. Today, we'll talk about what is Hugo and what can it do. Later, we are going to take a look at how Hugo can be configured and how does a test flight using Hugo look. Furthermore, we are going to discuss how is Hugo made and how it impacts both the society and the environment. So let me begin with what is Hugo. Hugo is a disruptive solution in the aerospace field. It aims to democratize high-speed subsonic testing. It is a 50-kilogram flying testbed that can reach a speed of Mach 0.75. It is cheaper to rent than a wind tunnel and is versatile enough to host a large scale of experiments. It runs completely on sustainable aviation fuel and has a lot of advanced sensor suite on it, such as dual LiDAR sensors, strain gauges, and everything that the researcher needs to test their experiments. Now let's take a closer look at how this aircraft actually looks like. Hugo is a high wing configuration aircraft. This wing is fitted on the top of the fuselage on a fixed modular wing port. That means you can change the wing for another wing based on your experiment needs. Furthermore, it features a fixed modular canard board that can be used to attach a canard for more maneuverability. But at the same time, you can also fly completely without the canard and use just the cover. Furthermore, the aircraft features a retractable landing gear that is necessary for the high-speed flight regime, and also a modular tail cone, again, if you want to test different scenarios. Finally, the aircraft features 2 micro-turbine jet engines that each generate slightly over 100 newtons of thrust, making sure that the aircraft can achieve its high-speed flight regime. Now that we had taken a look at Hugo, let me introduce Plamena, and she will discuss what Hugo can do.
Thank you, Adam. So, now that we have seen just how cool and innovative Hugo is, So, now that we have seen just how cool and innovative Hugo is, we can move on to what Hugo can actually do. Starting off with the aeroelastic experiments. Hugo can be tailored for testing both gust load elevation as well as active flutter suppression. Or, in plain English, when intense turbulence tries to shake the aircraft apart, Hugo's wings can react in a matter of milliseconds in order to dissipate the vibrations. In addition to that, there's aileron reversal testing. At very high speeds, the aerodynamic forces can twist the wings in such a way that when we want to turn to the left, the aircraft would actually go to the right. Hugo faces this head-on by proving that the control system can mitigate this twisting. Moving on to the control system experiments. Hugo can be adapted to test for both innovative leading-edge controls as well as folding wing tips. Yes, actually, wings with tips that can be unfolded and folded in flight can be sent to us by the researchers for testing. But this is just half the story. Hugo is a modular beast, meaning that we can swap out the platform as required. That is why we set the baseline with our standard platform, from which we can obtain the baseline data. Then we flip the script with our canard configuration. By installing the mini wings at the front, we can test for extreme maneuverability as well as enhanced stall performance. Finally, we looked at the horizon with our truss-braced wings, which is the configuration on which global airliners are betting to lead to significant fuel savings. Now that we have gone over all of the experiments that Hugo can perform, it is time to see how Hugo will be configured. Everything starts with Hugo's plan for envelope. Initially, we looked at stubby aerobatic wings with aspect ratios as low as 5. Then we extended this towards high aspect ratios wings, reaching up to an aspect ratio of 27. Finally, we explored a range of sweep angles up to 20 degrees and various airflow parameters. So, what does all of this mean for our customers? Well, if they can dream up a wing within these ranges, Hugo can test it at Mach 0.75. Once we have the configured wing, we can begin with the standard analysis procedure. We first assess the wing structure, the aerodynamic loading, the buckling behavior, and the maximum deflection that will occur in flight. We then move on to the flutter analysis, the outcome of which is the flutter speed. This helps us verify that the proposed concept can operate safely within our flight envelope. Finally, we look at the stability and control. We reached out to the developer of Flow 5 and used the software to obtain accurate data on Hugo's eigenmotions. Now, buckle up, because we're about to take you on a ride through what a typical flight day looks like. Everything starts at Den Helder Airport, which is strategically located just 5 kilometers from the North Sea. Once Hugo is configured, the ground crew is in place, and we're ready for takeoff, Hugo can begin its 30-minute mission and climb to flight level 270, where there's no risk of bumping into commercial airliners. Off it goes. Once we reach the test location over the North Sea, Hugo can achieve a maximum speed of 0.75 Mach for a test window of 5 minutes. What outstanding performance. But what happens when a researcher approaches us and wants us to test the aeroelastic behavior of their wing platform? Well, how would Hugo obtain all of the required data? Hugo is equipped with a camera at the tail location, which is used to monitor the wings in flight. In addition to that, there's a LiDAR sensor, which is used to measure the deflection of the wings due to the bending and twisting. Also, several 6-axis load cells are positioned at the wing and fuselage interface in order to obtain the wing loads. And finally, along the wing of Hugo, we have positioned several strain gauges in order to measure the surface strains. Now that the first flight test is over, Hugo lands and is ready for reconfiguration. Could one of our skilled technicians help me out with this? Now we're going to swap the wings of Hugo. Perfect, thank you. Now, Hugo is ready to test both stable and unstable flight regimes. So, how are we actually capable of alternating between stability conditions in flight? For that, we can use Hugo's fuel tanks. By pumping fuel from the front tank towards the aft one, we can effectively shift the center of gravity of the entire aircraft as requested. Wow, what a day it has been. Once Hugo is ready to land, it begins its descent towards Den Helder Airport. But oh no, the operator missed the approach. What can we do now? Fear not, because Hugo has a fuel reserve for a total of 4 go-around attempts, ensuring that at the end of the day, Hugo can land safely. The best part of all of this is that each Hugo can perform up to 4 of these flight tests each day. That is a massive amount of daily data. Finally, when Hugo has safely landed, it is stored in a hangar at Den Helder and awaits its next mission. Now that we have seen how Hugo operates, Carl will walk you through what is Hugo made out of.
Thank you very much, Flamina. So, at this point, hopefully we all have an understanding of what Hugo is going to do and a broader sense of what Hugo is. But let us go a bit more into detail on what Hugo is made of and how we're going to make the different components. So, most of the material used for our aircraft were composites. We chose those material based mostly on its great strength to weight characteristics. And let us look at specific subsystems. First, the wings. We chose a carbon fiber reinforced polymer skin with a foam core. We chose this configuration because we knew that we had to develop and design a lot of different wings with a lot of different aerodynamic characteristics. And the idea was that we would create a foam wing and then put the carbon fiber on top of it, thereby easing production and again speeding up the implementation of the researcher's idea. The next point is our fuselage and empennage. We are planned to make this a monocoque structure, and again a outer carbon fiber layer, a honeycomb middle, and then finally a carbon fiber structure layer in the middle, or inside of the structure. This is a sandwich panel, and again made to ensure the structural integrity of our aircraft in all phases of operation. Then finally, the 2 most important systems where we used metal was the landing gear, since this needs to be able to withstand the impacts at landing, and the engine pylon, where it needs to be able to withstand the loading delivered by the turbine and also the thermal loading delivered by the turbines. Thereby, a nickel alloy steel was chosen to use this. Now, you might be thinking at this point, okay, I understand the concept, but how is this ever going to be legal? How can we do this? Well, we had the same question in the beginning of this project. So after extensive communications and conversations with experts from EASA, the European Aviation Safety Agency, we were able to find and make a roadmap of the certification and the usability of our aircraft. The first step would be to get a type certificate for Hugo. Having this would make Hugo airworthiness, or give Hugo airworthiness. Our Hugo aircraft would be designated as a light UAS, SC light UAS, and would be categorized in the high-risk category since it's operating at such high speeds. But again, then a major issue is, of course, well, the entire point of our aircraft is a researcher should be able to make changes, and they should be able to make major changes. So in this way, we needed additional methods to ensure our aircraft could operate legally and safely within the European Union. For that, we used the design organizational designer approval, the DUA, where we would get the permission to implement changes within our own organization, thereby sort of being within the umbrella of our design and our airworthiness approval in the beginning, instead of constantly getting our aircraft certified. This would also be known as research procedures, and again, enabling an operation and usage of our aircraft in these conditions. So, now we have shown you how it works and that it can work. A next important part is, of course, looking at what will the impact of Hugo be. Well, there are several ways to evaluate the impact of a system. And we started by looking at the impact it had on its surroundings. One of the major things would be the noise generated by this aircraft. This is a very fast aircraft powered by 2 turbines, so it became important for us in the beginning to model the noise during an entire test phase. As you can see on the slide, this is a spectrum of the noise generated by an aircraft paired with the frequency level at the noise occurring and the sound pressure level. This enabled us to generate a range of expected sound pressure levels and expected noise during the entirety of the operation, where we would arrive at a value in between 80 to 90 decibels. So of course, this is not going to be a completely silent aircraft, but we're not going to be deaf by standing close in the vicinity of it. Next, we designed this entire aircraft to be entirely SAF-powered. We did this because we had the intention of mitigating and lowering the emissions generated and connected to the operation of our aircraft. And again, we also wanted to quantify the impact of our system. Therefore, we performed a life cycle assessment of the system and was able to find that the complete emissions of our aircraft throughout its 15 years lifespan and operation would be around 700 tons of CO2. So again, not a huge amount, but again, something that we now have clarified and found. The next point, where we hope perhaps the impact will be even larger or more tangible, is in the field of research. Again, I could spend the entire afternoon discussing all the different ideas, configurations, and control systems we could test and implement with Hugo. But again, for the sake of brevity, I've chosen to focus on high aspect ratio wings. This is a technology and a design method where there are huge promises for reduction in fuel spent during flight. Current industry estimates say that up to 8 to 10% of fuel burned or used during flight can be removed with the implementation of higher aspect ratio wings. And this is something during our design and our report, we found that Hugo would be able to contribute significantly during the research and development of these systems. And finally, it is our belief that due to the modularity and versatility of Hugo, we would be able to decrease research time. Because again, you don't need to produce your entire aircraft to test one specific phenomenon. You can just give us that, and hopefully this should lead to shorter research time and thereby a faster implementation of potential safer and more fuel-efficient technologies. So we have now arrived at the end of our presentation. So finally, first, let's summarize what Hugo is. Well, Hugo is a high-speed aircraft operating at Mach 0.75. It is completely unmanned and working autonomously during the testing phase. It is a general aircraft, meaning we had designed it with modularity and versatility in mind in all stages of our design process. And finally, it is an observatory. We are able to create and measure high-quality research data using the advanced sensors that is spread out on the aircraft platform. Now, it's also relevant to talk about what Hugo can do. Well, Hugo can aid the analysis and development of novel wing configurations. Hugo can be certified within the EU and the Netherlands and be flown safely within the regulatory bodies of the European Union. And it can be powered by sustainable aviation fuel all throughout its operation. And finally, it is with our current estimate, we see that Hugo can slash research costs with almost 40% compared with traditional wind tunnel methods. So, where do we go from here? Well, we have arrived at the end of the DSE. The next phase, we will start by creating a higher detailed design. This design can then be used to create a prototype which can be used for testing. After the testing phase, we would be able to move on to the manufacturing and certification of our aircraft. And again, when we have certified our aircraft and manufactured it, then we would be at the operation phase, which with our current estimates would be around 2031. And now I would like to welcome all my colleagues onto the stage. And if you have any questions for me or my colleagues, please feel free to ask them.
Oops, sorry. I don't need this.
Okay, who comes up with the very first question? Peter.
So thank you very much for your presentation. The question I have is, what will be the acceptance process you will impose on the person that comes with a good idea for a wing to put it on your model? Because it happens that I made a wing in my garage and I would like to test it on your Hugo. What do you want me to do? Do you want me to do wind tunnel tests and other testing before it goes into your Hugo?
Thank you very much. Just for the people watching at home, I'll repeat the question. The question was, how do we...
I think the microphone is still off. Can you move that up?
Hello? Yes, perfect. So for those watching at home, I'm going to repeat the question. The question was, how do we make sure that the people that will test on our aircraft are trustworthy? How do we make sure that whatever they design will not cause any issues when tested with Hugo? And for that, I believe my colleague Marek will be the best person to answer that.
So, thank you, Arturo. And let me remark that if you have already made a wing in your garage, it might be a bit too late to contact us. Usually, you should start your conversation with us at the design stage, because we are interested, first of all, if your geometric parameters of the wings are within our platform envelope. We have checked this platform envelope for guaranteeing both sufficient aircraft performance, low enough mass, and controllability and stability. So if you're falling outside of this envelope, there is a good chance that it might just not be compatible. Then we are also interested in the wing cross sections that you are going to use, because while it's kind of hard to place geometric constraints on the wing cross sections, we do expect a certain minimum performance. We are pretty lenient with it, however, certain minimum performance of the wing cross section has to be there. And then we have already run preliminary simulations that within our bounds, the wings that you can put will fly with Hugo and can be flown in a stable and controllable manner. However, you still need to fit within those bounds. Furthermore, we need to check that there are basically the transonic performance of your wing is not going to cause any trouble, that you more or less know what you are researching for. If you are planning to do something that's relatively unsafe, unproven, we might just ask you to first place the smaller version of your wing in the canard port. Does that answer your question?
Let's say that I make my wing in my garage and we manage to fly it, but it breaks. So the aircraft crashes over the ocean. Are you still able to recover the data from the crash so that we can analyze what failed and what happened?
Perfect. So for those watching at home, the question was, if in any case the aircraft were to catastrophically fail and it would not be physically recoverable, do we lose that data or can we get access to it afterwards? So for most of the test flights, we will be transmitting data live. So on one side of things, the operator needs to be able to see what's going on in front of the aircraft, but also because of the short turnaround time when we do experimentation 4 times a day, we want to make sure that we're getting data as things are going. We have a replaceable storage device within the aircraft, but at least some sort or some degree of data you would be getting live. Does that answer your question satisfactorily? Perfect. Thank you.
Next question.
Yes, we use wind tunnels for a very good reason, because we know exactly what the air is doing. So now you're flying above the North Sea or wherever you're flying at high speed. The sun is shining, there are gas, there are whatever. How do you know that your experiment, that you can correlate your experiment in the end to something that you want to build in real life?
So the question was, wind tunnels are a known measure. We know how wind moves within a wind tunnel. How can we make sure that the data that we get from Hugo is then reproducible in a larger scale aircraft? And for that, my colleague Vaibhav will answer the question.
Thank you for your question. Although wind tunnels do have a lot of advantages like perfectly clean data and very predictable results, they also have certain downsides, for example, the wall interference, as well as not being able to test very long horizon experiments, such as what you would need for control systems. Additionally, flutter dynamics and such structural experiments are really hard to test in wind tunnels where your model is mounted in a very rigid point. So there are also a lot of disadvantages to wind tunnels, which just really flying an aircraft solves. Does that answer your question?
Yes, but then I have a follow-up.
Mm-hmm.
If you then talk about flutter and Sparky, of course, you have there a small aircraft. Your stiffness of your wings and your controls, everything, are completely different than if you talk about a commercial aircraft or bigger scale, so to say. Can we really, those highly dynamic effects, can we really do this? Translate your small scale, low scale, small size scale model translated into big aircraft?
Absolutely. So for the ones at home, since our aircraft is small, how can we be confident that we can correlate our smaller scale effects to a larger scale aircraft? I believe the answer to that is that we would be using this Hugo to validate our internal models, right? So if you model your aircraft in your program as a smaller aircraft with the structural properties of Hugo, you can validate that model against real world data, as most experiments are done, wind tunnel or not.
Now I say, but then I can just do a model and just change the parameters by making a Python script that runs me all the different variations, etc., and do some CFD analysis, and I'm done. And what is your answer then? What are you adding here?
I believe you would like to validate that with real world data, and that is eventually always the end goal of any experiment. So we believe Hugo will aid in validating for real world data.
Okay, thank you.
Yeah.
Okay, next question.
You mentioned that the engines will be self-powered. I heard stuff is expensive. So how do you think the wind tunnel will be cheaper than the wind tunnel experiments for customers?
So for those watching at home, the question was, we will be powering Hugo with SAF-powered engines, and SAF is expensive. So how can we back up the fact that Hugo will be cheaper than a wind tunnel when we're using SAF? So from our preliminary calculations, we have found that wind tunnels can cost up to 40,000 euros per flight day, and based on our fuel costs as well as the manufacturing costs and certification costs, we estimate the price of Hugo per flight day to be around 25,000 euros. So having run all of the calculations and the operational expenses as well as the capital expenses, we believe that we still have a significant margin within those to undercut wind tunnels quite significantly. Does that answer your question?
I have a follow-on question. How many runs do you do in a day with your engine compared to the wind tunnel?
So the question was, how many runs do we do per day? We
Compared to the wind tunnel.
compared to the wind tunnel.
So we have 25,000 euros per day. We fly how many times?
So the Hugo is set up to fly at least 4 times per day.
So 4 times 5 minutes.
Yes.
5,000.
Yes.
20 minutes. So it's what it is times 375,000 euros per flight hour.
Yeah, those numbers would be accurate. We do believe that the quality of data you would get out of Hugo would be more accurate. So scale models exist. Many companies, NASA, a lot of research institute create scale models to test what they can no longer test within a wind tunnel. The TU Delft itself, for the Flying V, made a model of the Flying V and flew it to obtain data. So we believe that in that sense, Hugo's high cost per hour is also backed up by the additional quality of the data you would be getting in comparison to what you would see within a wind tunnel. This is a scaled down factor, but scale factors are calculatable. You can find non-dimensional values, and then you're flying the real thing. So you understand you understand the interaction between the wing and the fuselage, as well as any other component that you might want to try within the flight dynamics of an entire vehicle. Does that answer the question?
One more small. How many hours do I get for 40,000 euros of wind tunnel?
Um,
You know that?
Guillermo, would you know the value per se?
It's about a day. You get
You would get about a workday worth of.
So 1 hour versus 8 hours
Yes.
wind tunnel.
Additionally, we found that most wind tunnels charge wind on time. So you have a lot of setup costs. So if you're just there to set up your experiment, you have to pay for that. As well as if you're turning the fans on, you would have to pay additional fees for that. So 40,000 euros is the lowest estimate for the base price of a wind tunnel we could find. Yeah.
Don't know whether you have already a sale concluded. Yeah, next question. Okay, lady.
Hi, first of all, thank you for the presentation because the visuals were very, very nice. I have a question regarding your choice in terms of how you do the stability of the aircraft and if you have considered fuel sloshing and how that affects your performance and stability.
So for those watching at home, the question was, with regards to the stability of our aircraft, have we considered fuel sloshing and any other possible implications from internal components? And for that, Alex will answer.
Thank you very much for your question. Well, inside of the aircraft, we actually have 2 fuel bags that we are using in order to accommodate for the CG excursion. And the fuel bags have been equipped inside with linings, so slashing does not occur. We have thought of this phenomenon, and since we do not have a lot of fuel inside, the sloshing would not go out of the CG excursion parameters that we have already set for the aircraft. I hope that answers your question.
So the question was, Hugo has been designed for a Mach 0.75 flight speed for air elastic analysis. And the question was, how hard would it be to modify this design to be able to go slightly faster, correct? For that, Matic will answer.
Thank you. And the answer is, it's technically possible. For now, we have mostly analyzed the design because it's just the preliminary design for our standard operational envelope. However, given that we have both excess space for fuel and excess engine thrust, it is definitely possible to go above Mach 0.75. However, there you might start experiencing the transonic shocks. I think from your question that you actually want to experience the transonic effects. However, then we might not allow you to use the full envelope because we will have to ensure that combination of your airfoil and sweep is sufficient to have predictable transonic effects that we can actually fly it safely without a too huge chance of it crashing. Okay.
Okay, last question, keep it short. I keep it short. You made a proposal for making your fuselage from composite with a honeycomb structure, but you have a circular versus really some conical shapes. How do you plan to do that? And why not just a simple monocoque? Some frames, some stiffness.
So for those at home, the question was, we are using a carbon fiber monocoque, and we have a lot of complex shapes. So how do we justify the use of composites instead of a simple fuselage monocoque? Why did we use a sandwich? In comparison, in relation, sorry, instead of just a carbon fiber skin? Perfect. Clement will answer.
So thank you for your question. But since most of our design was actually based on local loading, it turned out that the skin thickness that we would require was very low, like below 1 millimeter. And in order to prevent the plane from buckling only by us picking it up, we had to reinforce the core of the structure itself. That is why we decided to have an outer skin of carbon fiber, a honeycomb core of thickness of about 10 millimeters, and an inner skin, again, of carbon fiber. Yeah, and it also has an amazing stiffness to weight ratio, which is also very beneficial for our design. Yeah. Does that answer your question? Thank you.
Okay, thank you very much. Give them a big hand. Okay. Now the moment is there that quite a few of you are going to receive a diploma. But I first want to give the floor to the principal tutor, Saulo Castro, to address you as a team. Hold both of them in one hand.
Thank you, Joris. So, congratulations everyone that you've reached this point. I don't know if you remember about 2.5 years ago when we were in the end of the dynamics course, where I showed a picture of the DSE group that I had tutored, the last one usually. And then I used to say in my lectures, oh, this will be you in 2.5 years. So here you are now, right? So time goes really fast, and I must congratulate you to have survived the bachelor. That has a very high pace here at TU Delft. And I'm always happy to see you finishing your studies and being more ready for the world now with your technical skills and also interpersonal skills, being able to solve problems that require a lot of uncertainty or that involve a lot of uncertainty. That's one of the features we are most proud of our Delft students, that are able to solve things with a lot of uncertainty. So yeah, I can just say I'm very proud of you. And now also ready to hand you the diplomas.
Okay, we have one person who's not yet ready for the diploma, but is close. So we're going to give him already the folder to put it in. Vayab, be ready. Please come forward. And if you want to take pictures, please do so. Almost there. The first diploma is for Arturo Arends Martinez. If you want to come down for a better picture, please do so. We have plenty of time. And then we also have a folder for you to store it in safely.
Thank you.
Next one, Guillermo Castro Lima da Silva. Yeah, take as many pictures as you like. Here's the folder to put it in. Plamena Dainlova Dimitrova. Including a fan club. So you brought your own fan club, I heard. And here's the folder to put it in as well. Alexandru Georgiou. Yeah, all pictures taken. Yeah. Don't forget the folder. The next one, Adam Janicek. Yes, and the folder. Next one, Hanna Maria Skrobanek. And the folder, of course. Next one, Karl Georg Müller-Vistisen. And the next one is for Theo Sokonai. Oh yeah, and you have to look very carefully at this diploma because this is a cum laude diploma. And here's your folder. And the last one, which is also a cum laude diploma, Marek Ryska. Yeah, enough pictures. And the folder, of course. please take a seat because I have a couple of announcements to make before I let you go. Yeah, please take a seat. First of all, congratulations to all the young graduates. Well done, I would say. However, this comes as a word of caution. You have now a diploma, and this is the only one you will get. If you lose it, if you ruin it, if you spill beer on it later today, you will never get a new diploma. That's why we gave you a folder to put it in safely, so guard it with your life. If you lose it for that reason, we can give you a statement that we once have given you a diploma, but there will never be a new diploma. If you really want a new diploma, you have to do the whole program again. So, be careful. What's going to happen the rest of the day? There is, in 2 more rooms, there's still presentations after this one. In the meantime, we're setting up the reception. It's going to be a bit of a mix of outdoors and indoors, seeing the fact that it's still pretty warm outside. We will do the award ceremony outside around 5:30. By then, the square in front of the building is in the shade, and the wind should have turned to the western direction, so bring a tiny bit of coolness from the sea. But we can also imagine that this is too much for you, so what we also do, we'll live stream it to this lecture room. So then you will be connected to the square with some delay, so you heard the applause first there, and then you can applaud yourself here. Take off your jackets when you go outside. Shorts are also fine, because it's really, really hot. And if you feel too warm, we have the lecture room still open, where it's still cool. In this room, we're going to have some other diploma ceremonies. I would like you to evacuate the room so that we can set it up for another diploma ceremony. You can leave the room via that door, but also upstairs, because it's going to be crowded here, I guess, so you can also leave upstairs. That said, I'll see you later today. For jury members who have finished, please give me your results before you leave this room. If you're not finished, then you can take it to the other room, but if you have finished, please give me your results. Thank you very much.